Welcome to DAR Tutors. Today, we're beginning our study of complex numbers, a topic that is fundamental to IB mathematics applications and interpretation HL. We will explore how complex numbers arise naturally from quadratic equations that have no real solutions, and how they provide a complete framework for number systems. Our goal is to develop a strong conceptual and operational understanding of this essential concept. Let's start with a foundational concept: the quadratic equation. The general form of a real quadratic equation is a x squared plus bx plus c equals 0, where a, b, and c are real numbers and a is not 0. You'll recall that the solutions to this equation are found using the quadratic formula. The formula states that x equals negative b plus or minus the square root of the discriminant, all divided by 2a. The discriminant, which we call delta, is defined as b squared minus 4ac. The value of this discriminant, delta, tells us about the nature of the solutions. If delta is positive, we get two distinct real solutions. If delta is 0, we get one real solution, sometimes referred to as two equal or identical solutions. And most importantly for today's lesson, if delta is negative, the equation has no real solutions. This last case, where delta is negative, is what prompts the introduction of complex numbers. The core question is, what does it mean to take the square root of a negative number? Mathematicians faced this very question. How can we extend our number system to include solutions for equations like x squared equals negative 1? To answer this, they defined a new quantity, an imaginary number, represented by the letter I. This number I is defined as the square root of negative 1. The key property of this number is that when you square it, you get negative 1. In other words, I times I equals negative 1. This single definition allows us to take the square root of any negative number. Let's see how with an example. Consider the expression the square root of negative 81. We can rewrite this as the square root of 81 times the square root of negative 1. The square root of 81 is 9, and we know the square root of negative 1 is I. So, the result is simply 9i. Let's try another one that's a bit different. What about negative the square root of negative 3? The negative sign outside stays there. Inside, we have the square root of 3 times the square root of negative 1. This simplifies to negative I times the square root of 3. We typically write the I before the radical to avoid confusion. So, we have successfully expressed the square roots of negative numbers using the imaginary unit I. This is a crucial first step. Now let's see how this imaginary unit I helps us solve quadratic equations that previously had no real solutions. Remember, if the discriminant delta is less than 0, we can now use our new rule for square roots of negative numbers. Let's work through an example. X squared plus x plus 2 equals 0. The coefficients are a equals 1, b equals 1, and c equals 2. We will use the quadratic formula. Plugging in our values, we get x equals negative 1, plus or minus the square root of 1 squared minus 4 times 1 times 2, all divided by 2 times 1. Simplifying the expression under the radical, we get the square root of 1 minus 8, which is the square root of negative 7. This is where our new number system comes in. We replace the square root of negative 7 with I times the square root of 7. The solutions are negative 1 plus or minus I times the square root of 7 all over 2. This can also be written as negative 1/2 plus or minus I times the square root of 7 over 2. We now have two solutions, just as the quadratic formula always promised. These numbers, of the form a plus bi, are called complex numbers. They are the solutions to all quadratic equations, regardless of the discriminant. So let's formalize what a complex number is. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers. We call a the real part of the number and b the imaginary part. For a complex number z equals a plus bi, we use the notation re of z for the real part a, and im of z for the imaginary part b. It's important to remember that the imaginary part b is a real number. It's the coefficient of I. Let's look at an example. For the number z equals 2 plus 3, the real part, re of z is 2, and the imaginary part im of z is 3. This definition is incredibly powerful because it encompasses all the numbers we've worked with before. If we choose the imaginary part b to be 0, we get a plus COI, which is just a real number. If we choose the real part a to be 0, we get 0 plus b, which is bi, a purely imaginary number, Therefore, the set of real numbers is just a subset of the complex numbers. Complex numbers provide a complete system. An incredibly useful tool in working with complex numbers is the complex conjugate. If we have a complex number z equals a plus bi, its complex conjugate, written as z star or sometimes z with a bar on top, is a minus bi. All we do is change the sign of the imaginary part. For example, if z is 2 plus 3i, its conjugate z star is 2 minus 3i. The real part stays the same, and the imaginary part is negated. The complex conjugate has a very special property, especially when we multiply a complex number by its conjugate. Let's multiply z equals a plus bi by its conjugate z star equals a minus bi. We can expand this using the distributive property, or notice that it's the difference of squares. This gives us a squared minus bi squared, which is a squared minus b squared times I squared. But we know I squared is negative 1. So this becomes a squared minus b squared times negative 1, which simplifies to a squared plus b squared. The result is always a real number. This property is crucial for division, as we'll see next. Now let's discuss how to perform basic operations with complex numbers. The rules for addition, subtraction, and scalar multiplication are quite intuitive. For addition and subtraction, we simply combine the real parts and the imaginary parts separately. Think of it like combining like terms in algebra. For example, a plus b, a plus ic plus di becomes a plus c plus b plus d. Scalar multiplication is just as straightforward. To multiply a complex number by a real scalar k, we multiply both the real and imaginary parts by k. So k times a plus bi becomes k plus kb. You distribute the scalar. Multiplication of two complex numbers also uses the distributive property. To find the product of a plus bi and c plus dii, we multiply each term in the first parenthesis by each term in the second, just like expanding binomials. This gives us ac plus 80 plus bci plus bd squared. The final step is to substitute negative 1 for I squared and collect the real and imaginary parts. The product simplifies to AC minus BD plus add plus BC TE. Remember, the key is to always simplify any I squared term, Now let's tackle division. This is where the complex conjugate becomes indispensable. When dividing two complex numbers, our goal is to eliminate the imaginary part from the denominator. We achieve this by multiplying both the numerator and the denominator by the complex conjugate of the denominator. The process is to take the complex fraction, a plus bii, divided by c plus dii, and multiply it by a cleverly chosen form of 1, the conjugate of the denominator, c minus di, over itself. This gives us the product of the numerators divided by the product of the denominators. We just saw that the product of a complex number and its conjugate is a real number. The denominator, c plus di times c minus di, will simplify to c squared plus d squared. So the division simplifies to the expanded numerator divided by c squared plus d squared. The result is a complex number in the standard a plus bi form. This technique is a cornerstone of complex number arithmetic. Let's work through a full example that uses all these operations. We will be given two complex numbers and asked to find their sum, difference, product, and quotient. Suppose z equals 3 plus 2i and w equals 4 minus i. We want to find z plus w, z minus w, zw, and z over w. First, the sum is plus w bus at 3 plus 2i plus our 4 minus i. We add the real parts to 3 and 4 to get 7, and we add the imaginary parts, 2i and negative I, to get I, so the sum is 7 plus I. Next, the difference is minus wbws, 3 plus 2i, minus 4 minus I. This is 3 plus 2i minus 4 plus I. Combining the real parts, 3 minus 4 is negative, so 1. Combining the imaginary parts, 2i plus I is 3i. The difference is negative 1 plus 3. Now for the product. As times wi is 3 plus 2i times 4 minus I. Using the distributive property, we get 12 minus 3i plus 8i minus 2i squared. Simplifying, 12 plus 5i minus 2 times negative 1. This is 12 plus 5i plus 2, which equals 14 plus 5i. Finally, the quotient. To find z divided by w, we have 3 plus 2i over 4 minus I. We multiply the numerator and denominator by the conjugate of the denominator, which is 4 plus I. The denominator becomes 16 plus 1. The numerator, when expanded, is 12 plus 3i plus 8i plus 2i squared. This simplifies to 10 plus 11i over 17, or written in standard form, 10/17 plus 11/17 I. You can use your GDC to check these results. Let's explore another important property. What happens when we add a complex number to its conjugate? Suppose we have a complex number z equals a plus bi. Its conjugate is z star equals a minus bi. Let's find their sum, z plus z star. We add the two numbers, a plus bi plus a minus bi. The imaginary parts, bi and negative bi, cancel each other out. We are left with 2a. Since a is a real number, 2a is also a real number. So we have proven that the sum of a complex number and its conjugate is always a real number. This is a very elegant result. Take a moment to consider. What would happen if we found the difference between a complex number and its conjugate, that is z minus z star? Let's work it out. Says minus z star equals a plus bi minus a minus bi. This expands to a plus bi minus a plus bi. Here the real parts, a and negative a, cancel. We are left with 2 bi. This is a purely imaginary number. So the difference between a complex number and its conjugate is always purely imaginary. We've focused on the mechanics of arithmetic. Now let's look at a fundamental concept of algebra, the equality of complex numbers. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. In other words, a plus bi equals c plus di if and only if a equals c and b equals d. This seems intuitive, but it's a powerful tool. It allows us to turn a single equation involving complex numbers into a system of two real equations, which we can then solve. Let's see this in action. We need to find the real numbers x and y that satisfy the equation x plus 2i times 1 minus I equals 5 plus y. Our strategy is to first expand the left side to get it into a plus b form. Expanding the product, we get x minus xe plus 2i minus 2i squared. Substituting negative 1 for I squared, we get x minus xe plus 2i plus 2. Now we group the real terms and the imaginary terms. The real part is x plus 2, and the imaginary part is negative x plus 2 times I. So the left side is x plus 2 minus xi. Now we can apply the equality rule. Our equation is now x plus 2 minus xe equals 5 plus y. For these to be equal, their real parts must be equal and their imaginary parts must be equal. This gives us a simple system of two equations. From the first, x equals 3. Substituting this into the second, we get y equals 2 minus 3, which is negative shot to 1. So the solution is x equals 3 and y equals negative shot 1. This method is incredibly useful for solving many types of problems involving complex numbers. So far, we've thought of complex numbers as algebraic expressions, but they also have a powerful visual interpretation. We can represent any complex number z equals a plus bi as a point, a, b, in a coordinate plane. This plane is called the complex plane or the Argand plane. It looks a lot like the Cartesian plane you're familiar with, but the axes have different names. The horizontal axis, corresponding to the x-axis, is now called the real axis. The vertical axis, corresponding to the y-axis, is now called the imaginary axis. To plot the number a plus b, i.e., we find the real part a on the real axis and the imaginary part b on the imaginary axis, and that is our point. Every real number a has an imaginary part of 0, so all real numbers lie on the real axis. Every purely imaginary number bi has a real part of 0, So all purely imaginary numbers lie on the imaginary axis. The origin, Torodaro, represents the number 0. There is a deep connection between complex numbers and vectors. We can represent a complex number z equals a plus bi not just as a point, ab, but as a position vector from the origin to that point. This geometric interpretation is incredibly useful for understanding addition and subtraction. The Argand plane gives us a beautiful geometric interpretation of complex conjugates. Remember, the complex conjugate of z equals a plus bi is z star equals a minus bi. Let's see what this looks like geometrically. We can plot both z and z star on the same Argand diagram. Suppose we have a complex number z in the first quadrant. Its coordinates are a, b. Now let's plot its conjugate z star. Its coordinates are a, negative b. Notice that the real part a is the same for both points. The imaginary part b has the same magnitude but the opposite sign. What is the relationship between these 2 points? They are reflections of each other across the real axis. This is a powerful geometric insight that can help visualize complex numbers and their properties. Now, let's connect this back to our property that z plus z star is always real. When you add 2 vectors, you add them tip to tail. Geometrically, z plus z star would be the vector from the origin to z, and then the vector z star from the tip of z. Because z and z star are reflections, adding them geometrically would result in a vector that lies entirely on the real axis, which corresponds to a real number. Just as with vectors, we can interpret the arithmetic operations of addition, subtraction, and scalar multiplication geometrically on the Argand plane. Let's take an example. Suppose z1 is 4 plus I and z2 is negative 1 plus 2i. Let's find z1 plus z2 algebraically and geometrically. Algebraically, it's straightforward. z1 plus z2 is 4 plus I plus negative 1 plus 2i. This simplifies to 3 plus 3i, so the resulting complex number corresponds to the point 303. Now let's see this on the Argand plane. First, we draw the vector for z1 from the origin to the point 4, 1. To add z2 geometrically, we draw its vector starting from the tip of the z1 vector. So from 4 to 1, we go left 1 unit and up 2 units. This lands us at the point 3, 3. The resultant vector, which starts at the origin and ends at 3, 3, represents z1 plus z2. This is identical to adding vectors tip to tail. Subtraction can be visualized similarly. To find z1 minus z2, we first consider the vector for negative z2. If z2 is kish 1, 2, then negative z2 is 1, 2. We then add z1 and negative z2 tip to tail. Starting at the origin to 4, 1, we go right 1 and down 2. This gives us 5, 1. The resultant vector represents z1 minus z2. This geometric interpretation provides a deeper understanding of complex numbers and their operations. Let's summarize the key concepts we've covered today. We started by seeing how complex numbers resolve the problem of taking the square root of a negative number, allowing us to find solutions for all quadratic equations. We defined the imaginary unit I as the square root of negative 1, with the property that I squared equals negative 1. This led to the definition of a complex number in the form a plus bi, with a real part and an imaginary part, and its conjugate a minus b. We then saw how to perform addition, subtraction, multiplication, and division, with division requiring the use of the conjugate. And finally, we learned to visualize these numbers and their operations on the Argand plane, with the x-axis representing the real part and the y-axis the imaginary part. This framework, from algebra to geometry, is the foundation for our continued study of complex numbers, which you will find have countless applications in engineering, physics, and other fields. Now, it's time to test your understanding with some practice problems. Let's work through a few examples in an IB-style question format. Here's the first question. Pause the video and try to solve it on your own before watching the solution. Given the complex numbers z equals negative 1 plus I and w equals 3 minus 2i, find the value of z minus 3u, expressing your answer in the form a plus bi. First, we substitute the expressions for z and w into the problem. We have negative 1 plus I minus 3 times the quantity 3 minus 2i. Next, we distribute the negative 3 across the terms in the parenthesis, being careful with the signs. This gives us negative 1 plus I minus 9 plus seki. Finally, we collect the real terms and the imaginary terms. The real part is negative 1 minus 9, which is negative 10. The imaginary part is I plus 6I, which is 7I. So the final answer is negative 10 plus 7I. This problem tests your ability to perform scalar multiplication and subtraction. Let's move on to our second problem. Again, I encourage you to try it yourself first. Question 2 asks us to find the exact value of the product of negative 2 minus 3i and 4 plus 5i. We need to express it in the form a plus bi. This problem tests your multiplication skills, including handling negative signs correctly. We expand the product using the distributive property, also known as FOIL. Negative 2 times 4 is negative 8. Negative 2 times 5i is negative 10i. Negative 3i times 4 is negative 12i, and negative 3i times 5e is negative 15i squared. Now we simplify. We combine the imaginary terms, negative 10i and negative 12i, to get negative 22i. And we substitute negative 1 for I squared. This gives us negative 8 minus 22i minus 15 times negative 1, which is negative 8 minus 22i plus 15. Collecting the real and imaginary parts, negative 8 plus 15 is 7. The imaginary part remains negative 22i. The final product is 7 minus 22i. Our third question is about division, which is a bit more involved. Take your time to solve it. Question 3 asks us to find the exact value of the quotient, negative 1 plus 2i divided by 2 minus I, giving the answer in the form a plus bi. The key here is to use the complex conjugate of the denominator. The denominator is 2 minus I, so its conjugate is 2 plus I. We multiply the top and bottom of the fraction by 2 plus I. Now we expand the numerator and denominator separately. The denominator, 2 minus I times 2 plus I, is the difference of squares, which simplifies to 2 squared minus I squared, or 4 plus 1, which is 5. The numerator expands to negative 4 plus 3i, so our fraction is negative 4 plus 3i divided by 5. In standard form, this is negative 4/5 plus 3/5 I. Our fourth question combines several concepts. Give it a shot. The problem states that a plus b squared equals negative 16 minus 30i and asks us to find the possible real values of a and b. This problem uses the equality of complex numbers. First, we'll expand the left side. Expanding a plus b squared, we get a squared plus 2ab plus b squared. Substituting negative 1 for I squared, we have a squared plus 2ab minus b squared. Rearranging to standard form, we get a squared minus b squared plus 2abi. Now we equate the real and imaginary parts of both sides of the original equation. The real part on the left is a squared minus b squared, which must equal the real part on the right, negative 16. The imaginary part on the left is 2ab, which must equal the imaginary part on the right, negative 30. This gives us a system of two equations. Let's solve the second one for b. From 2ab equals negative 30, we can write b as negative 15 over a. We can then substitute this expression for b into the first equation. This gives us a squared minus the square of negative 15 over a equals negative 16. Squaring the fraction gives a squared minus 225 over a squared equals negative 16. To get rid of the fraction, we multiply the entire equation by a squared. This results in a to the fourth minus 225 equals negative 16 a squared. Rearranging, we get a to the fourth plus 16a squared minus 225 equals 0. This is a quartic equation, but notice its form. It's quadratic in a squared. Let's make a substitution. Let u equal a squared. The equation becomes u squared plus 16u minus 225 equals 0. We can solve this quadratic for u by factoring. Factoring gives us u plus 25 times u minus 9 equals 0. So u equals negative 25 or u equals 9. Since u is a squared, we must have a squared equals 9 because a is a real number and its square cannot be negative. From a squared equals 9, we get two possibilities for a, 3 or negative 3. Now we find the corresponding values of b using b equals -15 over a. If a is 3, b is -5. If a is -3, b is 5. These are our two possible pairs of solutions for a and b. Our final question is a prove that question, which is common in IB exams. It asks you to explain a geometric property. Question 5 asks you to explain, with an illustration, why the difference between a complex number z and its conjugate z star, written as z minus z star, is always a purely imaginary number or zero. What distinguishes these two cases? Let's begin with the algebraic proof, which we explored earlier. Let's write a complex number z as a plus b. Its conjugate is z star, or a minus by. The difference, z minus z star, is the quantity, a plus b minus a minus b, which simplifies to 2b. This result has a real part of 0 and an imaginary part of 2b. Thus, it is purely imaginary. The result is 0 only if the imaginary part is 0. 2bi equals 0 only if b equals 0. If b is 0, then z is a real number. Z equals a. In this case, z star is also a, and their difference is a minus a, which is 0. So the result is 0 precisely when the complex number z is real. Otherwise, it is purely imaginary. Now for the illustration on the Argand plane. Let's draw a complex number z in the first quadrant. This is a vector from the origin to the point, a, b. We also draw its conjugate, z star, which is the reflection of z in the real axis. The expression z minus z star can be rewritten as z plus negative z star. To find this geometrically, we find the vector for negative z star. This is the vector z star reflected through the origin. Now we add z and negative z star tip to tail. Starting from the origin, we go to the tip of z at AB. From there, we draw the vector negative z star, which goes from AB to AB plus negative AB, which is 0 to b. The resultant vector, from the origin to 0 to b, lies entirely on the imaginary axis. This represents the number 2bi. The only way for this vector to be 0 is if its length is 0, which means 2b is 0, so b is 0. This geometrical representation perfectly explains the algebraic result. This concludes our introduction to complex numbers and the Argand diagram. Mastering these concepts is essential for success in IB Mathematics AIHL. Understanding how to represent complex numbers, perform operations, and interpret them geometrically will open the door to many advanced topics in mathematics. If you're looking for more personalized help, contact DAR Tutors for expert tuition in IB A-Level and IGCSE curricula. Our team can provide the in-depth support you need to achieve your academic goals. Thank you for watching. Welcome to DAR Tutors for online and home tuition. In this video, we'll explore complex numbers, a fundamental topic in IB mathematics. Applications and interpretation higher level. Let's start with the definition of a complex number. Here, A is the real part and B is the imaginary part. Let's look at some examples. We can also define the complex conjugate. For example, if ZL2 plus 3D, then its conjugate Z is 2D or 3D. Now let's move on to operations with complex numbers. Addition and subtraction are straightforward. Multiplication involves distributing terms and using the property I2 to 1. Division requires multiplying by the complex conjugate of the denominator. Let's work through an example. For part A, we add the real and imaginary parts. For part B, we subtract the real and imaginary parts. For part C, we multiply the complex numbers. For part D, we multiply by the conjugate of the denominator. Let's move on to the equality of complex numbers. Here's an example of how to use this property. For part A, we first simplify the left side. Now, equating real and imaginary parts, we find x and y. For part B, we expand the left side. Equating real and imaginary parts gives us a system of equations. This concludes our introduction to complex numbers. DAR for expert tuition in IB A-Level and IGCSE curricula, contact DAR Tutors.